Algebra 2. This is the video that accompanies A9, verifying inverses. Remember last assignment had us finding inverses, right? So we replaced the y's and the x's and solved for y, and we found inverses by doing that. Today we're verifying them, and I will just remind you what an inverse does here. So we have an x over here in the domain of our f. We act on it with our function f, and we end up with an output, what we would call an f of x, right? A function g is its inverse is if we evaluate the function g at f of x, we should get back where we started. I gave a couple examples of this with numbers when we were finding inverses, but this is real generally. It's like knocking them all down, a row of dominoes down, right? We do it for one general x. And likewise, if we are acting on things that look like f of x with g, this must be the domain of g, and this must be its range. And just how we can do a cycle with x in the domain of f, we can do the same thing with x's in the domain of g. That is, we act on the function x with g, we get something that looks like a g of x, it's a y value, it's an output, and then we act on it with f, and we get right back where we started. So, remember last week we did composition of functions, and this is how we verify that f and g are indeed inverses. We do f composed with g, and when we do that, we should get x. And we check both of them. It should also work the other way. G composed with f of x is equal to x. Okay, so that both of these have to be true for f and g to be inverses. So, example 1 says verify that they're inverses. Verify they are inverses. So, verify they're inverses. So, in the past, if you make a mistake and you can't get to it, in the past people have told me, oh, I couldn't get to x, so they're not inverses. No, they are. If you can't verify when it says verify, you're doing something wrong. So let's do f composed with g of x. Remember, f composed with g of x says evaluate f at g. G is x plus 5 over 2. So that is our input into the function f. When we give you an input for x, you multiply it by 2 and add 5. So we have 2 times x plus 5 over 2. Oops, there should be a minus somewhere in this example, I bet you. Yeah. 2x minus 5. See, they're not inverses. So, 2 times x plus 5 over 2 is x plus 5. We still have this minus 5 here, so it works. Now the other one, g composed with f of x. G composed with f is the function g evaluated at f now. So we have g of 2x minus 5. Check out the rule for g. Here's your input. You put it right there, add 5 divided by 2. So we have 2x minus 5 plus 5, all divided by 2. 2x minus 5 plus 5 is just 2x. 2x divided by 2 is x. And there you go. You verified that these are inverses. You'll always be able to get back where you came from. Next one is a little different. It asks, are they inverses? Are f and g inverses? Example 2. We have 3x minus 3 and 1/3 x plus 4. Well, let's just do f composed with g and see what happens. F composed with g is f evaluated at g. G is 1/3 x minus 4 plus 4. And the rule for f is multiply your input by 3 and subtract 3. So we have 3 times 1/3 x plus 4 minus 3. Distributing gives us x plus 12 minus 3, or x plus 9. You did not get back to x, so f and g G are not inverses of each other. Okay. So, one more, verify that F and G are inverses, example 3. This is an interesting one because it says here that F and G are inverses only for x greater than or equal to 0. And why that is because this is a quadratic. This is x squared is the parent function. We've multiplied it by a number so that horizontally compresses it, and then we lower it down one. So the graph of this thing looks something like this. From last lesson, we know that a function's inverse is not a function if the original function does not pass the horizontal line test. So this original function does not pass the horizontal line test, so its inverse would look something like this. It's not a function. So what they have done here for this problem, notice, is they've said that x can only be greater than or equal to 0. So this branch, if you will, this branch of the quadratic function, we're just not dealing with it. So now we can find an inverse that does pass the vertical line test, and so the inverse is a function. So this is a domain restriction. Okay. Sometimes people will ask me, well, will ever one of these work and not the other? You know, and I will say that yes, sometimes you will get stuck with one composition and not the other, and that is a domain problem most likely. Okay, so they've restricted the domain for us here. So let's do it. F composed with G. F composed with G, remember, is F evaluated at G. Square root of x plus 1 over 2. The rule for F is square it, multiply it by 2, subtract 1. So we're going to do 2 times the square root of x plus 1 over 2 squared minus 1. X plus 1 over 2 squared, you got it, x plus 1 over 2. 2 times x plus 1 over 2 is just x plus 1. We still have this minus 1 out here, and we've verified that way. G composed with F, I don't want to do that. G composed with F, we are going to evaluate G at F. F is 2x squared minus 1. Okay, so we're going to put that 2x squared minus 1 into the function G. Here's your input for G. So we have, what is wrong with my equal signs? The square root of 2x squared minus 1, that's your input, plus 1 over 2. Oh, minus 1 plus 1 is just 2x squared over 2, which is just x squared. The square root of x squared is x. Just positive x here, remember that our domain is restricted. So we verified that they're inverses. F composed with G was x and G composed with F is x. I hope you like this. Remember, composition of functions is another operation. You didn't have it before. So now you have some more operations than the plus, minus, multiplication, and division that your classmates in the shorter halls have. Good job. I love you.